Welcome to the data visualization in RStudio tutorial. So in this video I'll go over the three main visualizations or plotting functions that we deal with in RStudio in this course, and talk a little bit about what sorts of variables or what data types are most appropriate for each visualization. Again, one of the things that you need to understand or start to learn is identifying your variables, your variable types, and then what's the most appropriate visualization given those data. And so this tutorial is to help you understand that. Excuse me. So again, the first thing we're going to do is set our working directory. We can either do that with the set wd command. I can run that, right? Or we could go to session, set working directory, choose directory, and navigate to our folder, right? Again, one of the best practices is to have a designated folder or working directory that you're going to use for this course in RStudio, so that you can keep all of your data files, scripts, images all in one place, and that you sort of get into the routine of downloading the data, moving it to that folder, and having everything all in that directory, so there's no issues with RStudio. Excuse me. So the first thing we're going to do is bring in a data set. So I'm just going to call this plant.data. So I'm going to name the object here, and I'm going to assign to less than dash, and then read CSV function. Excuse me. And so I'm going to bring in this CSV data set, 105 observations of two variables. Okay? So if I view that data, again with a capital V, i.e. W, that should open it up. So now I have two variables, plant treatment and health improved. So it's either treated or not treated, and improved or not improved. So that was my data, 105 observations. I could do the summary of that data, right? So they're both characters. Okay, so these are both categorical variables. And so when I have both my independent and dependent or categorical variables, the most appropriate visualization for that data is going to be a mosaic plot, or what we sometimes call a contingency table. And so we want to look at sort of the counts or proportions of each of the categories across the two variables. So the first thing I'm going to do is create a table. So if we looked at, let's look at the data again. So again, it's treated, improved, not treated, improved, right? So we have 105 observations. What the table function is going to do is condense that into counts. So how many were treated and improved, how many were treated and not improved, how many were not treated and improved, and not treated and not improved, right? So we want to get some counts. So we can do that with the table function. We list our variables, so we want our row variable to be listed first and our column variable to be listed second. So in this case, plant.data, $ health improved. So this says the data set, $ the variable. And again, RStudio will help you complete this. And then comma, so this is our row variable, and then plant.data, $ plant treatment. So now whether it's going to be improved or not improved will be the rows, and whether it was treated or not treated will be the columns. I could flip that if it makes more sense, right? But in the table function, we always list the row variable first and then the column variable. So if I run that, now we can see down here in my console, improved, not treated, treated, and we get some counts, right? So 26, 35, 29, 15. Okay. Now what I want to do is create an object of those counts, because right now I have not created, really stored that in RStudio. So I'm going to create an object called counts, and then do the same thing. So counts here is my object assigned to, and then table, the same previous command. I can do this before I don't have to do table on its own. I just wanted to show you the table function. But I need to create an object in RStudio that has those counts assigned to it. And so I'm going to do that. So now we can see that counts pops up here in my environment. Excuse me. The other thing we often do with categorical data, if we're making a mosaic plot, is sometimes we want to graph the counts. Sometimes we want to graph the percents, and so I can create an object called percents equals to 100 times the prop table of counts. So it's the proportion table of counts, and it's a 2 by 2 table, right? So I can create this, and now I have an object called percents. So I have an object called counts that is the physical counts, 26, 29, 35, 15, and an object called percents, which is the percentage of those, right? So 47.3, 52.7, you notice how those sum to 100, and then 70 and 30, okay? Now to visualize it, I use the bar plot function. Again, this isn't going to make a bar graph, this is going to make a mosaic plot, and we can do it a couple different ways. So I'm going to use bar plot and then open parentheses, then I want to tell it what I want to plot. In this case, I'm going to do percents, but I could change that to counts if I want, right? Then comma main axes or main graph title, plant treatment versus health improvement, except I should probably spell improvement right? Again, all in quotations. You notice how it turns out green on my screen because it's going to be putting that out. The comma X lab, again the X axis label, in quotations plant treatment, comma COL for color equals C, which is concatenate, that's assigned to, or not really assigned to, but make a list of, and then dark blue and red. Again, remember I can use this colors command to look at all the possible colors. And again, remember that RStudio will assign the treatments in alphabetical order, right? And so dark blue would be the first one, alphabetically, red would be the second. If you want a certain color to a certain treatment or a certain category, you have to make sure you put that in the correct order. Then comma. Then I do, so when we make a mosaic plot, oftentimes the legend needs to be sort of moved around a bit, so there's a little extra coding here. Legend equals row names, and then I'm going to use counts. You could technically use percents, it's the same table, right? But we want our legend to be our row names, so that would be improved, not improved, right? And then comma, and then I'm going to tell it where to put the legend. Args, so args.legend equals list, open parentheses, x equals top left, okay? So this would be left, right, center, bottom left, top left. So you might have to do this a couple times depending on how your legend looks, right? So often you won't know what the table or the plot looks like until you finish it. You might have to go back and move the legend so it's not in the way. Horizontal, so HORIZ equals true. I could also put this as false if I want my legend to be vertical. Close parentheses, comma, beside equals false. So I'm going to show you this visualization in a couple ways. Basically, we can put our bar plots on top of each other or next to each other. This beside equals false would stack them. So here, I'm just going to run this. And we can see now it spits it out right here. So we've got not improved, improved. Those were our row names, and not treated, treated, right? We've got our X label as plants treated. I could also put my Y lab equals, in this case, percent, right? And I could try it again. Now I've got a Y label in here, okay? But there are a few things that make this not too pleasing, right? So first thing I'm going to do is show you this beside. So if I change false to true and then run it, now look what happens. Now it moves the bars next to each other rather than stacking them, right? So still the same, not treated, treated, improved, not improved, right? Still everything else the same. It's just whether we stack those bars or put them side by side, right? hence the code beside. Do we want our bars beside each other? Yes, that would be true. No, we want them stacked. Beside would equal to false, right? Now, if I just change this horizontal to false, now we can see that my legend is now vertical rather than horizontal, right? And maybe I don't like where it how it looks right there, so I'm going to move it to the top left now, and we can see how that looks. So again, I can change where the legend is, whether it's horizontal or vertical, and whether my bars are stacked or not. And certainly I could change colors. Again, this whole list of colors, right? 655 different colors, as long as you spell them correctly. Okay. But again, we can go through and tweak our visualization to make it look like we want to. And again, then we would export this to save as an image to be used in our assignments later on. Okay. So let's clear this. Now I'm going to move on to the next data set. In this case, this example is going to be roach.data, again assigned to read CSV. So I'm going to bring in a new data set, and let's just see what that looks like. I have 156 observations of 2 variables, species and mass-specific VCO2. So my species variable is categorical. It's either a dubia, a dB, or a hisser, or a red runner. So dB, HSRR, and then mass-specific VCO2 is a continuous numerical variable. So I have one categorical and one numerical variable in this case. Okay, again, if I look at the structure, species is character, right? And that's numerical. Okay? So in this case, when I have a categorical independent variable, species is independent, and a numerical continuous dependent variable, I want to do a box plot. Okay? So I'm going to use the box plot function here. This is a function that creates a box plot when your y variable is continuous and your that's your dependent, and your x variable or your independent is categorical. Okay, we can do this with 2 groups or with 200 groups, right? So it doesn't matter if you're doing a t-test or an ANOVA, as long as you have your dependent is continuous and your independent is categorical, you want to use a box plot. Okay. So we do box plot as a function, open parentheses. Now we're going to tell it our y and our x. So we list our y variable first, and then the tilde. So notice this tilde right here. So here, mass-specific VCO2 is our dependent or continuous y variable, and then we do the tilde, and then species is our categorical independent variable on our x-axis. Okay. Comma, then we got to tell it the data that we're using. Data equals roach data, comma, here's our y label, comma, x label, comma, main axis or main visualization title, comma, col, again color equals concatenate, and then in this case I have 3 species, so I picked 3 colors because I'll have 3 levels or 3 categories: green, blue, and red. Again, done in alphabetical order. My categories here are DB, HS, and RR. So green for dubia, blue for hissers, red for red runners. Okay. So if I run that, this is what I get, right? So here I've got my title, my y or x-axis label, my y-axis label, a box for each one. The black bar in the box is the mean. The bars here indicate the sort of the range, and the circles there are the outliers outside of sort of the range. Okay. But again, whether we have 2 categories or 200 categories, whether we're doing a t-test or ANOVA, as long as our y variable is continuous and our x variable is categorical, a box plot is the most appropriate visualization to do. Okay. There are some ways we can alter the way the boxes look. But we're really not going to get into that now. You can certainly Google that and play around with it, but it makes this line of code much longer. And again, I hit return here just so that you can see it. You can write this in one long continuous line, just making sure we have commas in the right place and closing the parentheses after we're done. Okay, one more data set and one more example. I'm going to bring in an object called chirps. So now I've got 15 observations of 2 variables. If I look at this, I've got chirps and temperature. Both of these variables now are continuous numerical variables. So we went from categorical and categorical to numerical and categorical. Now we've got 2 numerical variables. So again, if I look at those, they're both numerical, only 15 observations of each. So the most appropriate visualization when both of my dependent, independent, or continuous numerical variables is a scatter plot. Okay. So I started with bar plot, then box plot. Now I'm just using plot. Okay. So plot, open parentheses. Now I'm doing my y tilde x. Okay. So I want the chirps, which is chirps per minute. It actually is chirps per second in the data, actually. So I'm going to change that real quick. Okay. So that's my dependent variable on the y-axis is chirps per second. The x variable is temperature, again separated by the tilde. Now in plot, I can actually list the x first if I want. So chirps is a data set, $temp, then a comma, then the y variable. Okay? Or I can list y tilde x, comma, and then the data set. So these will give you the same thing, but you have to make sure you put the y and the x on the right axes, otherwise you're graphing it incorrectly, and then if we go to do a regression on top of this, our regression line won't work because we most likely will have the formula correct in our regression function, but not in our plot function. So again, if you're going to use a tilde here, you have to list the y variable first and then the x. If you're going to separate them with a comma, it's the x variable first and then the y. Okay. Then my x-axis label here, again in quotations, my y-axis label, so comma, so xlab equals, and then in parentheses, or quotations, whatever I want, comma, ylab equals, again in quotations, whatever I want it to say, comma, main, the main title of my graph, equals, again, whatever I want it to say in quotations, comma. Then we get this last part here, PCH equals, and you'll see these on some other course documents. PCH is telling it what we want the point character to look like. Do we want it to be triangles, diamonds, open, closed? So I think there's 0 to 25. We can change this value from 0 to 25. Each one of those numbers is associated with a different shape. And so I'll show you in a second what happens when we change that. Then comma. LWD is line width. How thick do we want the line on our points in our scatter plot to be? I usually like 1 or 2. 1 is default, so I can leave this out. It will just be 1, but sometimes you need to make those lines a little thicker to stand out, and so you can put LWD equals 2. You can go higher than 2, is just remember that gets really thick and tends to make it a little blurry, comma, and then color equals blue. What color do we want our points to be? Okay. And then we close the parentheses. If I run this, now look at over here, cricket chirps per second versus temperature. And now I've got blue open triangles with sort of a nice thick border. Okay. What happens if I change a couple of these things? Let's change that to 3, this to 1. Otherwise we're on the same end. Now I've got thinner line and plus signs or crosses. If I go that back to 2, see again that's changing the line width. If I change the PCH number, again all it does is change. Now I'm on X's, 5, right, and diamonds. Right. Again, the second one is just the second plots command is showing you when we put the X first, comma, Y. Okay. Again, the rest of the code is the same. Here I'll just change the color. Okay. Let's change PCH to 13 and you get something like that, right? So again, the code allows us to sort of customize our visualization to what we think looks best. But those are the three main plot functions we will be using this semester. Each one is most appropriate for a specific combination of variable types: categorical, categorical, numerical, categorical, numerical, numerical. Part of what you need to learn this semester is when to use which plot or visualization, and then how to do it correctly in R.